All right. Hello, everyone. I'm very happy and excited to be here at REcon, especially because the last REcon last year was my first ever attending the cybersecurity conference. So now I'm very happy to present one of my projects exactly 1 year after. Thank you, thank you. All right, so let's jump right back in. Oh, can I see the slide? Right. So in this session, I will showcase how I found multiple vulnerabilities within the Linux kernel itself and in third-party Linux kernel modules in a very easy manner. And hopefully, by the end of the session, you will be able to see and to do it yourself as well. So my name is Tal Lossos, and I'm a vulnerability researcher at CyberArk Labs, focusing mainly on operating system internals. And besides playing with kernels, I really enjoy and practice CrossFit. So what we will have on our menu today. So we'll first start by reviewing and talking a bit about open source vulnerability research methodologies, followed by how we can integrate the use of static code analysis within it. Afterwards, we'll see how I used static code analysis against the kernel itself and see some vulnerabilities I found. Lastly, by deep diving into the main vulnerability in the NVMe driver of the Linux kernel, and hopefully, if I sacrifice enough for the demo gods, it will work. So, some methodologies. So, again, when you're researching open source, the most straightforward thing you can do is just start reviewing and start searching vulnerabilities. Because unlike closed source research, you have the source code yourself. So you don't need to actually reverse engineering and everything, but maybe I will talk a bit about this more later. Again, when you're searching for the open source projects, you need to make sure that you're searching and you're having the latest and greatest code with you. Because there's a lot of times where the open source project distributes a little bit of code pieces between some repositories. So you need to make sure you have the whole source code, the latest, with you. Another very good thing about open source research is that if there's a piece of code that you might not fully understand, you can just ask your favorite AI chatbot, and hopefully it will answer your questions. And of course, the use of static code analysis, so whether it's your own tools or whether it's just popular tools already, are a thing. So it very helps you to find low-hanging fruits to start with, or just looking for maybe some leads in the projects. And of course, debugging and recompiling is quite easy in open source projects, again, because you have the source code, obviously. And if you found something, maybe a lead to some vulnerability, you can just add as many debug snippets as you want and recompile, execute it, doing whatever you want. But there's a little bit of disadvantages as well of open source research, which the first one is for the bug bounties. Because if you will find vulnerability within the Linux kernel, for example, you most likely won't get a bounty for it, unlike Apple and Windows of Microsoft. So that's a bit of a caveat if you like a bug bounty. And that's my own personal, from my own personal experience, open source research might be a bit of overwhelming. Well, I'm not saying that closed source research isn't overwhelming, but if you already have the whole source code with yourself, you might, again, that's my own personal experience, that I'm finding myself really wasting a lot of time of trying to understand code that might not really be relevant to what I'm currently researching, only because I want to see and to know how it works. So in my experience, it's a bit overwhelming, but again, of course, closed source research is overwhelming as well. So what's the general strategy of it? So as I mentioned earlier, first really we need to find the code itself, so whether it's in GitHub, GitLab, or whatever you're using. And afterwards, you can just start shooting some static code analysis. So whether you're reviewing it by yourself with your own eyes or using automated tools or whatever you want, just start looking for bugs. And after you found maybe a little bit of a lead or some minor bug, you can now start to compile, build, and execute it. So maybe add some debug snippets, the lovely printf statements. Yes, don't do it, but you can do it. And just debug and try to hopefully trigger the vulnerability or trigger the bug that you've just found. And lastly, after we understood a bit how our product works, we can maybe start to consider fuzzing, because now we know the expected structures and the behavior of the program. So now we can actually try to write our own maybe dummy fuzzer or something like that, or a more fully advanced fuzzer. And of course, we can just repeat the stages that we've done before. So if the bug that we found isn't exploitable, for example, we can now start by static code analysis again and everything. But we're in REcon, right? Like the reverse engineering conference, and I haven't mentioned reverse engineering once. So hopefully I will give you an example why still reverse engineering compiled binaries for open source, it's still important. So let's assume that we have this memcopy function. And you might think that, like, if we look at the disassemble code or the assembly itself, that it would look like preparing some stack and just calling memcopy and something. But let me show you otherwise. This is a bug I found last year, which is in the Razor's Linux kernel modules. And this function actually correlates, or its purpose is to change the RGB colors of your keyboard. And as you can see, it has a very, very simple vulnerability here in the memcopy. The start column and stop column is fully user controlled. And because of that, we have fully control over the size being used in the memcopy function. So we have a lovely buffer overflow in kernel, so this could lead to potential privilege escalation. And if we now shoot up some disassemble code, we might think that it will look like this. So this is somehow the expected disassemble code that we actually, maybe it's a bit similar to the source code itself. So we're just preparing some stuff and just, as you can see, just calling memcopy. But in my case, it actually looked like this. So as you can see, there is a new if statement that was inserted in compilation time, and this was actually a part of the 45 source mitigation, which purpose is generally to mitigate buffer overflows vulnerabilities. It came from GCC, but now it's been introduced into the Linux kernel. So as you can see, there's a new if statement that was inserted in compilation time, and it wasn't in the source code themselves. So there's a saying that I really like. It's that the source code itself, it's like what the developer intended the machine to do, but it's not what the machine will actually run. And if we want to see and to know what the machine will actually run, the only way to do it is by reverse engineering it, or the compiled binary, of course. And in this case, if we knew the compiler configuration, we might have known that this check will be inserted. But that's the reason that, again, you need to reverse engineer your binaries. So how we can use static code analysis to help us to find those bugs? So again, that's a very quick recap. Static code analysis by OWASP commonly refers to the running of tools that attempt to highlight possible vulnerabilities within the source code. Or in just simpler words, just finding vulnerabilities before running the actual program with the static code itself, with the code itself. But you don't have to write your own custom tools to do it. You can just shoot up your favorite package manager and download what's available for you. So if you're working in a C or CPP project, there's the Clang one or CPP check for Python, Pylint, MyPy, whatever you want. And of course, if I've mentioned static code analysis, of course that I had to mention CodeQL, but it's a bit different because its main purpose is about the query language itself and not about just shooting up the binary and give me some potential bugs, please. So that's the point of it. So how did I use static code analysis against the kernel? But we'll start first with what type of bugs I was looking after with the static code analysis. So it's quite obviously that static code analysis won't help you find, or maybe the more advanced one, won't help you find logical bugs. It will most likely help you to find memory corruption bugs. So just from general buffer overflow, integer overflow, underflow, null pointer dereferences, and uninitial variables. And one of the key aspects that I was looking after is to use the most simplest tool I could potentially find and find major vulnerabilities with it. And for that case, because again, I worked with a Linux kernel, I wanted to use the CPP check. So CPP check is a very, very, very simple but very good static code analysis tool for C or CPP projects. And it's very easy to use because after you download it, you can just run it from your CLI against your C source code, and it will show you potential bugs. And if you compile it from the sources themselves, you can do a little bit of more advanced stuff. So for example, here, I'm just doing the normal, give me some error from my C file, and then it has a built-in HTML parser that it can generate a custom HTML files from the potential bugs, and then you can just open up your default or favorite web browser with it, and then you can actually select which type of bugs you're looking after. So in this case, I was looking for potential null pointer dereferences bug. So I selected null pointer dereferencing operation. And maybe if there was a potential bug, it looks something like this. And then it showed me the code. And maybe it's a vulnerability. But again, we have to check it. So let's go to the fun part of the actual bug. So as you remember, this piece of code, again, that's a very simple memcopy vulnerability. And I wanted to see if I could find it in a faster way, because it took me some time to actually find it. And again, I wanted to use static code analysis tools, but unfortunately, the static code analysis tools that I've used didn't actually find these vulnerabilities. And I think because the tools themselves didn't know that the start and stop column, as I shown you earlier, that is being passed to the function, are user controlled. And I think because I won't really get into it, but this driver was being implemented via the sysfs in Linux, if you know it, and it didn't know to parse and to know that there are actually user control parameters. But again, I wanted to, I don't know why, I just wanted to find vulnerabilities with these tools. So fortunately for me, at that time, NVIDIA, the greatest, open sourced their Linux kernel drivers. So they were closed source for a very long time in Linux, and they decided to open source it. And you know, if NVIDIA wrote code, no way there's going to be vulnerabilities there, right? So apparently there were a few, and this is the first one. This is, for example, a function that is being run upon disconnecting the device. And as you can see, we don't actually need to know what the function does. We can just see that it's a vulnerability, because here at the top we're declaring a null pointer called device, and then if we compiled our binary with some configuration, we're calling a function ACPI bus get device, and then we're dereference it immediately. But even if we weren't compiled with this configuration enabled, you can see right after it's like null pointer dereferences, which is clearly a bug. And if you're not really trusting me, this is the definition of ACPI bus get device. And as you can see, it might return the device as null. All right, so I've shown you some vulnerabilities in Linux kernel modules. What about the kernel itself? So after finding the vulnerabilities in NVIDIA, I was very thrilled to see if I could find, again, by just running some CPP check and then checking the errors, manually, of course, if I can find vulnerabilities in the kernel itself. And around that time, there was a very driver that had a lot of drama around it, which was the NTFS implementation of Linux. And after it got introduced in the kernel, I think it was version 5.15, I'm not sure, it didn't get properly maintained. And you know, as an offensive perspective, not getting maintained rang a bell from me, and I said, all right, let's test it. And after running some static code analysis tool, I've encountered this lovely piece of code. Can you maybe spot a problem here? All right, I'll show it to you. So here, as you can see, we're declaring two pointers. The first one is being assigned to null, and the second one is uninitialized. And as you can see, we're just working with the pointer called utterB. So you see, we don't need to understand what the code does. Just look utterB, and I find utter, blah, blah, blah. And then if utterB not non-res, we're doing some operation with utter. Utter, we didn't change the utter value once. So yeah, that's clearly a programmer problem, because it meant to use utterB and not utter, and it was a very simple vulnerability, again, that was in the mainline for a few kernel version. And if you want more to read about it, my colleague Alon Zahavi wrote a very nice blog post about it, about how we found it and how we exploited, and go check it out, very lovely blog post. Right, so now let's go to the juice of the presentation. So again, after that, I proved that I can indeed find vulnerabilities in the kernel itself with the use of static code analysis. I wanted to find another vulnerability, but this time, I didn't tell you, but the previous vulnerability could have been led to a local denial of service attack, and I wanted to find another vulnerability, maybe here with a higher impact. And after, at the time, kernel version 6 was being introduced, the release candidate versions, and I read the patch notes, and there was this very nice patch notes about something about NVMe. I know what's NVMe, it's something maybe SSDs, I don't know, an in-bad authentication support. Again, I have no idea what it is, I just know NVMe, something SSDs. But as I mentioned already, we don't need to actually know what the code does or what we're searching, because we can just find bugs in the code itself. So after shooting up the CPP check, I got this error that there might be a potential problem here, and I got this lovely piece of code. Can you maybe spot the vulnerability here this time? While I'm drinking some water. So here, as you can see, there's this structure, CTRL, and it has a member underneath, which is CTRL key. And we're working a bit with it, calling some functions. And if there was a problem with this function, we're just reassigning the pointer to null, and then we're just dereference it in the log. Quite weird, no? Indeed, that's a problem. It was just, again, the developers forgot to do some cleanups, and it was in the main line. So it's pretty cool. But now, after we find a potential bug, we need to actually now know what we just work with, because if I want to exploit it, I need to know how to work with it, because I need to make a test, like a working environment and everything like that. So let's review a bit of what is NVMe at all. So the hard definition of NVMe is like non-volatile memory express protocol, which is a transfer protocol for accessing non-volatile storage media over PCIe. Or in simpler words, just access to your local SSDs over PCIe bus. Very simple. What's NVMe OF? So NVMe OF is an extension for this protocol, which allows you to access your devices over non-PCIe connections. So for example, accessing your SSDs over, for example, fiber channel or even Ethernet. And one of the implementation of it is NVMe TCP, which is the definition of the NVMe over fabric for TCP specifically. So if we're summing it up, NVMe is the protocol itself or the specification for accessing your SSDs over PCIe. NVMe OF is the extension of this protocol for accessing your devices over non-PCIe connections. And last one is NVMe TCP, which is the implementation of NVMe OF for TCP connections. But where can we find it? So we now know it's NVMe, but if it's indeed exploitable, where can we find it? So I was quite surprised when I searched like where NVMe exists, and essentially every big cloud provider has it by default. So for example, your local Linux machine on Amazon has their local storage stored over NVMe driver. So for accessing your EBS storage, it's over NVMe. The same for Azure. And if for some reason you don't like cloud providers, or you're working in an air-gapped environment, your lovely NetApp machine has it as well. And if you can see here, specifically for TCP, it mentions. And if you don't like storage at all for some reason, as I mentioned, your local kernel, favorite operating system ships with it by default. So if we have indeed a potential bug in such area, exploiting it, and if indeed it's exploitable, might be very risky. So now, how can we exploit it? So if we go back a bit, we had this null pointer dereference primitive in the NVMe setup auth function. And we know that we can actually trigger it if we fail the function NVMe auth extract key. So if we somehow, again, at this time, I don't know what even is a key, yes? But how can I make an invalid key? This is the function that's checking if a key is valid. As then you can see, if the key is not the simplest way to do it, if it's not in the length of 36, 52, or 68. So now we have that, okay, if we maybe can create some key that we don't know yet what's even a key, about in not of this length, we might be able indeed to exploit it. But so we might have a null pointer reference in the kernel, but for what, how can we exploit it in Linux? So fortunately or unfortunately for some people, there's quite a few mitigation in the kernels that prevent you from exploiting null pointer references bugs beyond a denial of service. And the first one is the mmap min address, which just won't let you to allocate addresses, low addresses. You have the smap and smap that if you were able to map those addresses, for example, the null address, the O address, you won't be able to actually access it and to execute it. And there's this concept in Linux which is called oops, which is like, it's similar to panic. Okay, so if the operating system, if the kernels knows that it might have a null pointer dereference, but it's still able to maybe somehow operate properly even after accessing this weird behavior, like I'm calling it low panic, low cure. But there's a lot of Linux distributions which are being shipped with an option which is called panic on oops, which if you will indeed have an oops, you still will get a full panic. And if you want to read more about it, there's a very lovely blog post by Project Zero, which explains, again, about this mitigation and everything, and how you can still exploit null pointer references in the kernel beyond a denial of service. All right, so how can we exploit our bug that we've just found? So if you remember the patch notes that I've just shown you earlier, There were quite a few of mention about TCP. Okay, so if they're mentioning a lot of time TCP, again, maybe there will be like some ringing. Maybe we have a remote primitive. Maybe from a denial of service attack, we might have a remote denial of service attack. So for that, we need to check out how it actually the NVMe system works. So if we look from the sources themselves, again, Linux open source, yay, we can see that there's two things. There's the host and the target. And the host is actually the client that requests the storage from our server, which in the NVMe system will be called the target. So again, we have our remote machine, which in the NVMe topology is called target, and our clients, our hosts, accessing it over the internet, over the connection or whatever it is. And in our case, it will be accessed over the TCP. And if indeed we're checking the vulnerable function that we've just found, again, it's called NVMe T setup auth, and the T stands for the target. Okay, so the vulnerable function that we've just found is actually on the server side, on the target. And just by the name of the function, we might start to thinking that maybe because it's in the setup authentication and the authorization authentication almost all the time it's at the beginning of the connection, we might think that it's indeed triggerable remotely by just trying to connect this to the machine. But again, we're in Linux, we have open source everything, so we can just go up the call stack, follow Elixir, click, 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 and after some clicks up, we've encountered this lovely function. And again, we don't need to know what it is, but just looking in it at the NVMe T REcon, we can see that it somehow resembles the first parsing function that gets the request, and now it tries to figure out what is the request. And if we're checking who is calling this function, we can indeed see that it's dependent of the NVMe over Fabric implementation. And as you can see here, we have the FC, which stands for Fiber Channel implementation, we have RDMA, and we have our lovely TCP implementation. And if we check the TCP implementation, we can indeed see that it's calling the kernel receive message function, which is the generic function being used in the kernel to read from sockets. So yeah, we might indeed are able to trigger this bug remotely. So now that we understood a bit, we can actually start to preparing an environment to test it out. So how do we make NVMe environment? So we know now what's NVMe, we know what's SSDs, TCP, but how we actually do it. So if we're searching online or on our beloved Google, we can indeed see that there's plenty of documentation how to configure your NVMe system and NVMe TCP system. And it's very easy. You have plenty of documentation, very simple. There's plenty of scripts that helps you. But if we're checking how to set up the authentication feature, which again, it just got introduced into the kernel, so there's no any documentation. But we're still able to figure it out by just reading the sources themselves. But again, it's quite hard, and the whole purpose of it, I wanted to find bugs in a very easy manner, and I didn't want to do the hard work. So after searching more a bit, I found this very nice block test framework, which is the block device test environment for the Linux kernel. So, maybe the programmers of the NVMe, the new feature, went and put some tests in this framework, and this is the GitHub page. And indeed, after checking the test, they made a test for checking this feature specifically. Okay, so now we don't only know how to set up a working NVMe environment, we can actually now set up a working NVMe environment with the feature of the authentication, which is vulnerable. So now I will show you a demo. Hopefully it will work. But again, I will explain what I will do. So I will have two machines. One sec, I will just show it up. One second, please. All right. So here on the right, on the right of your right, you have the NVMe server, which will expose the remote devices. And on the left, I have the machine that it will be allowed to access the machine. So here I have a script for configuring the environment. All right, so I've created my environment, and now as you can see, I will show you. This is just the configuration of the driver itself. And I have this test environment, and underneath it, I have the allowed hosts that are able to connect to this device. And again, because the authorization, I'm just in the server side, I'm saying which host is being allowed to access which network or which system. As you can see here, I have a host with 84678, which is it's exactly this, which is exactly this. Are you seeing? Is it big enough? You see? Okay, perfect. All right, so now if I have the working here on the right, now I will just try to connect to the system, again, which has the, obviously, the misconfigure invalid key. I will actually try to execute the connection. And here I will be using the NVMe binary, which is just the binary which I can use to communicate with my NVMe system. And hopefully, if the demo gods will allow, boom, it worked. Thank you. Again, very simple bug, and it was in the kernel mainline, so that's a bit, dodgy. Here I have, okay. So now we have this remote denial of service attack. But as I mentioned, we have to be configured on the remote system to allow to communicate with the remote server. So now we can only exploit it via a configured host, which is not, as an attacker perspective, it's not quite good. So I wanted to bypass this authorization feature. So firstly, I wanted to see how does the server side or the server knows what's my host. And in the NVMe system, the unique identifier in the system, it's called host NQN. And as you can see here, I just tried to access my remote server with a host called AAAA, and I got this error that my host isn't allowed to communicate with the remote server. So the first thing that I've done is just sniffing the network to see how does client sends, like what's my identification. And as you can see here, that's the raw packet that's being sent in clear text without any encryption or something, just sending, hey, I'm this host NQN, which again is the configured allowed host to access the remote machine. So if for some reason I'm able to send like my own connection packet from an unauthorized host with the host NQN that I will know that will be authorized, maybe I will be able to trigger it as well. But you might ask yourself, how can I even get the allowed host NQNs on the system? So for example, if working in a LAN environment, just a normal R poisoning attack or DNS poisoning attack will allow us to gain this kind of host NQN because these packets are being sent quite a lot of times, and it's very easy. And this time I will show you a remote demo. But I won't show you the network attack, but I will just show you how does it might look like. So again, it's quite similar to the demo I've just shown you earlier, but this time I have 3 machines. On the right side, I have, again, my own server that has the NVMe storage. On the top left server, I have the allowed host, okay, which is indeed configured to be allowed to talk with the remote server. And on the bottom left, I have the unauthorized host that I will try to trigger the functionality with it. So here again, I will configure. I'm configuring. Okay, the system is already configured. I'm showing you again that the allowed host ends with 84678, which is indeed the top left host. Oops. Just shooting up the kernel messages. Here now in the attacker machine, I'm showing you that indeed it has a different host NQN, which is currently not allowed to access the remote storage. As you can see, it's not 84678, it's something else. Here I will try to connect just the normal way to the remote machine, and this time I'm getting the not allowed, okay, because I'm not allowed to access the remote machine. But again, let's assume that I've just done the network attack, car poisoning, whatever it is, again, it's not very hard to do. And this time I will just copy, because I've gotten the host NQN, I will just use the allowed which again, in plain text in our local LAN, I will actually just use it from an arbitrary machine, and it will work. So now again, from a remote denial of service attack, by just knowing what's the allowed host, again, it's be able to do by just network sniffing, we're able to crash the remote server with any like arbitrary machine. So it's quite nice. All right, so after finding the vulnerabilities, I reported them directly to maintainers, and it was like all the vulnerabilities were fixed and patched immediately, and now you won't be able to exploit it again because it's patched. Multiple CVEs were assigned to the vulnerabilities, and there's a couple of more under disclosure. And I'm going to publish a blog post regarding the vulnerabilities with a deeper dive into them and exactly how, like, the journey that I've done in order to achieve those. Stay tuned for that. I'm going to publish it soon. And some wrap up. So again, open source research, again, from my experience, is a bit overwhelming. Of course, closed source as well. But so focus here is the key, like everything in life. So just make sure you're not wasting time at looking up for code that won't be relevant for you. Well, if you want to know how the whole project works, go for it, yes. But if you need to find vulnerabilities, it won't be good. If no documentations are available for whatever product you're researching, search for tests, because if you're searching for tests, you might be able to figure out how to set up a working environment, and it will help you gratefully. And the last thing is static code analysis is still a very powerful tool. All the vulnerabilities I showed you, except the Razor one, I found with the most simplest tool, all right? And it's crazy how many vulnerabilities I found with it. So it's just remember that it's a very great tool for finding low-hanging fruits. And if you're a developer, just make sure you use them in your CI/CD pipeline or whatever you do to make sure the bugs won't get into your product. And that's basically it. Thank you very much. Do we have time for questions or something?
Out of curiosity, how long was this vulnerable code part of the mainline? Because you'd think it'd be really short amount of time with so many eyes looking at it.
Yeah, which vulnerability is the NVMe one?
Any of them.
So the NTFS one, it got introduced, if I recall correctly, in kernel version 5.15, and it got fixed, I think, at kernel version 6.1. So quite a few of time. Again, very simple bug. And the NVMe one, I found it in the release candidate versions. So again, it's a mainline, you can install it, but I sent them the fixing patch before like the kernel version 6 was being released. So hopefully you won't be able to actually see it. So one of them a long time, one of them not a long time.
Hi. Thanks for the talk. It was really good.
Thank you very much.
So you showed some screenshots of the CPP, I don't remember the
Yes,
name of the tool.
CPP
Yeah.
check.
Yeah. And you also mentioned CodeQL earlier in the presentation. Did you find that?
I didn't. Sorry, finish your question.
Just did you compare the results between that or other static analysis tools?
I see. So again, the thing that I wanted to do is find them in the simplest way I could potentially find them. And CodeQL, for me, it wasn't only running a binary, so it was too tough for me, and I didn't want to use it. Basically it. Any other questions? All right, thank you very much.